Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 2 on interval notation. In the last lesson we talked about sets of numbers and how we could represent some sets of numbers by just listing the elements inside of them. That was what was called roster form. And then other types of sets, specifically sets that included stretches of the real number line, we had to use what was called interval notation. Interval notation can be a little bit tricky for students, and so there's another type of notation I want to show you today where you can represent chunks of the real number line in a bit of an easier way. Let's take a look at it. All right, so interval notation. We will often want to talk about continuous sets of numbers along the real number line. And again, I want to emphasize, the real numbers are all the numbers you know about. The fractions, the decimals, the whole numbers, the irrational numbers. And when you lump all of those things together, they fill in the entire real number line. There's no gaps, there's no breaks, there's nothing like that. All right, in the last lesson, as I mentioned, we saw how to represent those intervals along the number line using set builder notation. In this lesson, we're going to learn about something called interval notation, which is a fitting name, that will actually make representing these intervals or these stretches along the real number line in a much easier way. So let's take a look at how we do this in exercise number 1. It takes a little bit to get used to. So let's take a look at that. For each of the following intervals of real numbers, graph the portion of the number line described by the inequality and then write the set using interval notation. Okay, so great. In letter A, let's start with the most easy example of all. We've got a stretch that starts at -3, it ends at 5, and it includes both the -3 and the 5 because of those equal signs underneath the less than symbols, right? We would read this interval, by the way, by saying either x is greater than -3 and less than or equal to 5, or even more confusingly in my mind, some people read it as -3 is less than or equal to x, which is less than or equal to 5, which is basically just reading it from left to right. Now, how do I graph that interval on the real number line? Well, it starts at -3, and I'm going to put a closed dot there because of the equal sign. It ends at 5, which I didn't quite get on top of the 5, and then it's all numbers in between. Okay, so with interval notation, we'd have to have this curly bracket. We'd have to say something like, x is any real number with a vertical line such that, etc., etc. Here's how easy it is with interval notation. I'm going to write down the first number, -3. I'm going to write down the last number, 5, and I'm going to put what are called square brackets around them. Okay? I'm going to put square brackets around them. And what these square brackets mean is it means that the -3 and the 5 are included in the interval itself. Okay? Now, there's a difference when the endpoints, right? The endpoints are -3 and 5, when the endpoints are not included. And let's take a look at that in letter B. So in letter B, right, we've got this interval that goes from -6 to 4, right? Except the -6 and the 4 now are not included. So remember, when I'm graphing that, what I do is I put an open circle at the -6, I put an open circle at the 4, and then I color in everything in between them, right? Those open circles are saying that the -6 and the 4 aren't included. Now, how do I write this in interval notation? Well, I do exactly what I did before, which is put down a -6, comma 4, but now to show that the endpoints are not included, I put parentheses instead of square brackets. Now let's talk about the giant enormous elephant that just walked into the room, right? When you look at this, I would assume that every single one of you are thinking to yourself, that looks a lot like an XY coordinate point, right? X is -6, Y is 4. And it does. It looks identical to a coordinate point. So if you wonder, well, how will I tell the difference when somebody is talking about an interval versus when somebody is talking about a coordinate point? Well, the plain fact is the context will make it obvious. In other words, if you're in a situation where you're talking about intervals of real numbers and somebody shows you this, then they're talking about an interval. If on the other hand, you're plotting a bunch of points that lie on a line or some other type of a graph, well then that's going to represent a point on the graph. But the most important thing to understand right now about interval notation is that all you basically need to put down is the x value where you start, the x value where you end, and then you have to, use square brackets if the endpoints are included, and you have to use parentheses if the endpoints aren't included. Now, you can definitely have intervals like we have in letter C, where you've got one endpoint included and you have one endpoint that's not included. For instance, in letter C, right, we're going from -4 to 8, but there's only a greater than symbol there, or I guess it's a less than symbol from your perspective, and then from here, there's a less than or equal to. So the -4, right, that is not included, the 8 is included, and so that is our interval. How do we represent it with interval notation? Just like before, we put a -4 down, we put an 8 down. Since the 4 is not included, we put a parentheses, and since the 8 is included, we put a square bracket. Right? So this is completely consistent with what we saw in letter A and letter B, right? We take the number that we start at, the number we end at, we put a parentheses if that number is not included, we put a square bracket if the number is. Now, there's a few other considerations, right? Because the three examples we've seen so far, we've got a starting number and an ending number. But what happens if we don't particularly have a starting number and an ending number? Let's take a look at letter D, right? Here we have x is greater than or equal to 4, right? So the starting number is 4, and it's included, right? But then we're talking about all numbers to the right of it, okay? So what's not of question, right, if we're using interval notation, is that we should have a 4 as our starting number, put a comma. The 4 is included, so I'm going to have a bracket. The question is, what do I put down as my second number? Well, logically speaking, right, we should put the last number that this interval is going to hit. Well, there is no final number it's going to hit, but it is heading towards infinity, right? Infinity, way out there to the right. So that's actually what I'm going to write down as my second number. Now the question should become, should I put a closed parentheses, right? Should I put a bracket there, square parentheses, or should I just put a normal parentheses there? Well, what we say in math is that infinity and negative infinity, which we'll see in just a little bit, are never included as an endpoint because they can't be reached. All right? There's no point in time where this interval is going to stop at infinity because you can't actually reach the number infinity. So that will always then have a parentheses, right? You'll always have a parentheses. So we've got a 4 comma infinity where the 4 is included and the infinity never is. That one's pretty easy for students. Let's take a look though at letter E. This can be a little bit tricky when we have a less than. So in letter E we have x is less than 5. So again, simple enough. I'm going to put a circle on the 5. We've got a less than, so we're going to the left. Now, what that tells me is that I've got the 5 is my second number, and since it's not included, I'll put a parentheses there. Now, what is my beginning number? Well, again, my beginning number is the number that's way out here, and that's negative infinity, right? So that's actually my beginning number, and just like positive infinity, negative infinity can never be included. Simple enough. Now the last case, well, that we're going to be looking at right here is actually pretty easy. We've got x is greater than -4. So that means I've got a little circle on -4. I'm going to color everything to the right of it. That means my -4 is my first number, and I have a parentheses there because it's not included. Comma, my final number will be infinity, and also a parentheses because I cannot reach infinity. All right, so it's actually fairly simple when you've got, when you've got just like two normal finite numbers, right? Beginning one, -3, ending one, 7, right? And then you just have to decide whether they're included or not included, right? And keep in mind, right, These kind of brackets mean endpoints are included. Right? So in other words, you have an equal sign underneath those inequalities, and any parentheses, endpoints are not included. All right. Now that basically, more or less, is the entire lesson. We're just going to kind of get used to this notation as we move on. But any time that you need to represent, right, a continuous set of real numbers, it's got to be all real numbers. It can't be just the integers or just the rational numbers. Then interval notation is a very easy, quick method for representing those sets. Right? One of the advantages of the interval notation, as I mentioned, is all we need to know is the starting value, an ending value, and whether those values are included or not. So exercise number 2, building off what we just did, it says which of the following represents an interval equivalent to -12 is less than or equal to x, which is less than 4. All right, great. So this is simple enough. Pause the video and see if you can figure out which of these choices is correct. Well, this basically boils down to the brackets versus the parentheses, right? So we're going to use a bracket if the endpoint is included. We're going to use a parentheses if it's not. Notice that the -12 is included due to the equal sign there, but the 4 is not included due to no equal sign there. And therefore, the correct answer is choice 3. That's it. So the notation takes a little bit to get used to because you got to remember, oh, when do I use brackets? When do I use parentheses? And you have to avoid looking at something like this and thinking, oh, that must be a coordinate point. Even though it looks like one, it's not. Not in this context. All right, interval notation can be really, really nice if you're solving, like, let's say, a linear inequality, and you just want to represent the solution set. So let's take a look at exercise number 3. Solve the inequality given below for all values of x. Graph the solution set on the number line given, and write the solution set using interval notation. All right, well, I'd actually like you to do this. You can certainly do the first 2 parts, i.e. solving that inequality. That was from the last unit, unit 2. You should certainly be able to graph its solution set on the number line, and then take a shot at actually writing down what the interval is using interval notation. Pause the video now. All right, need to be a little careful because I've got a -4 sitting there. But for me, I'm going to rewrite this as -4x plus 12 is greater than 0. I'm going to subtract a 12 from both sides. And I'm going to get -4x is greater than -12. I'm going to divide by -4 on both sides. And immediately when I do that, I need to switch the direction of the inequality. And I'm going to get x is less than 3. All right, great, wonderful, right? On my graph, what that's going to look like is I'm going to circle the 3, and then I'm going to color in everything to the left of 3, right? Because x is less than 3. So hopefully you were able to do those 2 pieces very simply. Now, in terms of the interval notation, we've got to be a little bit careful here, right? The number that's on the right, is 3. And it's not included, so I have a parentheses. The number on the left is all the way out here at -infinity, and it is also not included. So our solution set really is all numbers from -infinity to 3, not including -infinity, and not including 3. That's it, right? Every number on the real number line between -infinity and 3 are a solution, but not -infinity and not 3. All right, let's keep going. Let's take a look. Interval notation can help us express values that a particular quantity or variable can have, right? And that's, again, it's really nice because we can avoid using the set builder notation that can get confusing and wordy and all of that. So let's take a look at exercise number 4 and watch for key phrases that we've seen in our inequality work. A recipe for a cake states that it must bake for greater than 30 minutes, but for at most 45 minutes. Write a set using interval notation for the amount of time in minutes that the cake can bake. All right, so I'd like you to pause the video now and see if you can write down an interval, right, of time for which the cake can bake using interval notation. Pause the video now. All right, well, they tell us the cake must bake for greater than 30 minutes, right? But at most 45 minutes. All right, now it's got to be greater than 30, right? So we certainly start at 30, but the 30 is not included, right? Because it's got to be greater than 30. If they had said at least 30 minutes, then we would be including the 30, but they don't. They say specifically greater than 30. Then they say, but at most 45, which means 45 should be included, but nothing above 45 should be included. So that is our interval. 30 to 45, where the 30 is not included, but the 45 is. Simple. You'd think that there'd be more work on this problem, but that's it. That's the whole problem. All right. We will sometimes want to be able to describe the x and y values that appear on a continuous graph. Interval notation will make this very, very easy, and we're going to see this a ton in future problems. So let's take a look at this. Exercise number 5. A line segment is shown graphed on the grid below. Letter A, state a set using interval notation that represents all x values that occur on this line segment. This is kind of cool, right? So for a graph, a continuous graph in the xy plane, there's a set of numbers that represent the values that x has, and then there's a set of numbers that represent the values that y has. The x values are a little bit easier, right? Because I can literally look at this graph and I can kind of drop down a line here and go, look at that, -3, and down here to 9. So all of the x values, right, go from -3 to 9. And I use brackets, right, not parentheses there, because there is a point where x is -3, right? -3 occurs on this graph as an x coordinate. And then the greatest x coordinate that occurs on this graph is 9. We can do exactly the same thing for the y. Let's take a look. That's in letter B. State a set using interval notation that represents all y values that occur on this line segment. All right, great. Well, I'd like you to pause the video right now and think about this a little bit. All right, well, let's take a look. So the top y value, the very biggest y value, is up here at 7. And the smallest y value is down here at 3. So the y values actually go from 3 to 7. Now it's very, very important. One of the things about notation in math is that there must be some kind of consistency about it, some kind of rules for its use and whatnot. When you are representing intervals of real numbers, you will always start with the smaller one and go to the larger one. So it's important for the answer here to be 3, 7, like that. You cannot have this. All right, that's not allowable. And it's not allowable because you're literally saying, oh, you know, I'm going to have all the values of x that go from 7 on up all the way to 3. Well, what would that mean? It almost seems like you'd have to wrap around infinity, you know, and that is definitely not what you want. So you can't have that. You've got to have values that go from a smaller value up to a larger value. All right, let's look at one last consideration. It's important to know when you can and when you cannot use interval notation to describe a set of numbers. So let's take a look at exercise number 6. Given the set represented on the number line below, explain why we could not represent the set using the interval 3, 12, where the 3 and 12 are both included. All right, well, pause the video now and think about this a bit. Why could we not use this interval notation in order to represent the set that way? All right, well, it's very, very simple, as long as you're comfortable with interval notation. Interval notation can only be used for a continuous set of real numbers, but this set only includes integers, okay? So maybe the best way to put it is interval notation includes all real numbers, but, our set is only integers. All right, and that's something very specific about interval notation. Interval notation, when you read something like this, that is every real number from 3 to 12, including both the 3 and the 12. On the other hand, this set of numbers is specifically just 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right? So we cannot use interval notation if we've got just integers, right? It represents all real numbers. But the great thing is that comes up a lot. All right, so today what we learned was how to use this new type of notation, and you have to learn a new type of notation all the time. In fact, a couple lessons from now, we're going to learn something called function notation, and it's also kind of a new sort of form of representing something in math. Here, this notation allows us to represent unbroken portions of the real number line by simply writing down the first number, comma, the last number, and then deciding whether or not those numbers are included or not included. Remember, the square brackets mean that the endpoints are included, the parentheses mean they're not included, and infinity and negative infinity are never included when you've got one of these intervals. All right, well, we'll get a lot of practice on this in coming lessons. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.